Welcome to part 5 of our discussion on nuclear chemistry. I am Engineer Elizabeth Espiritu, your facilitator. What is half-life? So half-life is the amount of time it takes for half of a given sample to decay. So each half-life, half of the sample decays and half remains. So half-lives vary from billions of a second to billions of years. It depends on what the isotope is. So for half-life, if we start with 1,000 activities, for example, after a half-life, the first half-life, the amount would be reduced to one half the original, so it becomes 500. And then in the next same amount of time, the amount would be reduced to half of what has been. So from 500 to 250, and after the same span of time, the 250 would become 125, and so on and so forth. So the level of radioactivity of an isotope is inversely proportional to its half-life, meaning to say, the shorter the half-life, the more unstable the nucleus. So the half-life of a radionuclide is constant. It's not affected by temperature or the number of radioactive nuclei that is present. Here are examples of radioactive isotopes and their half-lives. So of the isotopes that are in this list, the most unstable is phosphorus 28. So it has the shortest half-life at 0.27 seconds. And uranium-238 is the least unstable of them all. It has a very, very long half-life. So rates of disintegration reaction. So when we say rate, it has something to do with how long or how short the period of time before a radioactive nuclide disappears or reduces into some amount. So I'm not going to derive the mathematical formula anymore, but this is the result based on calculus and differential equation. So this is the relation between time and the amount of radioactive nuclide remaining after a period of time. So XO is the initial concentration of isotope X. X may be in mole or it may be mass. So it has something to do with the quantity of the radioactive isotope in mole or in mass quantity. Xt is the concentration of X isotope after a certain period of time. K is the rate constant. K is the rate constant and T is the time it takes for the radioactive particle to disintegrate. Okay, so we have a formula for half-life. Half-life is equal to natural logarithm of K. So the formula for the decay reaction is natural logarithm of Xt is equal to minus Kp plus natural logarithm of Xo. So if we are to rearrange the equation, we can make it into something like this. Natural logarithm of xt over xo is equal to minus kp. So look at this. If we are talking about half-lives of reaction, xt would be 1/2 of xo. So 1/2 xo over xo is equal to k, and t here would be the half-life. Half-life is represented by the symbol t 1/2. So 1/2 xo over xo, then xo, the symbols would cancel out. So we're left with the equation natural logarithm of 1/2 is equal to minus kt. So the equation becomes t 1/2 is equal to natural logarithm of 2 over k. So this equation would have come from here for half-life. Okay? So this is our formula for K and half-life. So if you are given the half-life of a nuclear reaction, then of a nuclear substance, then K can be calculated from it. Or if you are given K, the value of K for a particular nuclear reaction, then you can solve or calculate its half-life. So this is the formula for determining the half-life of a reaction. So let's apply these formulas in a sample problem. So in this problem, example number 1, americium is the radioactive isotope, has a half-life of 7,370 years. A sample containing 10 micrograms of this isotope, you are asked to calculate the mass in micrograms of the isotope that remains after 22,110 years. So this is the nuclear reaction. It releases big alpha particles. So you are given the half-life. Okay. If you are very good in math, you can easily see that 22,110 is one of the factors or multiples of 7,730 years. So 22,110 years divided by 7,730 years is equal to 3. So it's a perfect full number fraction. So that means to say there are 3 half-lives for americium, or 3 half-lives have been undergone by americium. So applying this to the concept of half-life, so for the first half-life, 10 microgram has been reduced to 5 micrograms. Sa second half-life, 5 micrograms is reduced to 2.5 micrograms. And in the third half-life, 2.5 is reduced to 1.25 microgram. So the answer is 1.5 microgram. So this type of a solution is a very simple solution if you are very good in mathematics and you can easily identify that these are multiples of each other. But unfortunately, not all problems can be solved that way. So there is an alternative solution to that. So I have shown you the formulas that you can make use of. So the formula for half-life as well as for the formula for the rate of reaction would be better to use for all kinds of problems that are similar to this one. So you are given the half-life. We make use of the half-life formula and we can solve for K. So K is equal to natural logarithm of 2, which is equal to 0.693 divided by the half-life is 7,370 years. So K has a value that is equal to 9.40 times 10 to the negative 5 per year. So the unit is per year because the unit of half-life is year. Okay, so we have solved for K. Let's make use of the formula for the rate of radioactive decay. Natural logarithm of xt is equal to kt plus natural logarithm xo. So xo is initial. This is the amount that remains after the passage of time. And time is given there as equal to 22,110 years. So let us substitute values and use the calculator to solve for this problem. And the answer is 1.25 microgram. And this is the same as the answer in the previous solution. So this is the end of part 5 of our discussion. I hope you learned something today.